sound you hear is the beat of a human heart. This sound is the heartbeat of the Atlas, United States Air Force. The performance of a guided missile depends on its complex electronic system. Every component, every connection must function properly the first time. The material given the responsibility of providing this electrical continuity is solder. Solder must bond together the thousands of small components and hold them through the strain and vibration of a missile flight. To do its job, solder must be applied properly. To use solder and to achieve the perfection demanded in airborne electronics, we must first thoroughly know and understand it. The art of soldering is known to have existed long before this book was written. The ancient Egyptians used solder to bond together pitchers and urns. Medieval cathedrals were adorned with the beauty of stained glass windows through the use of solder. Solder is one of the oldest, simplest, and most widely used metals in the world. Largely because of its simplicity, solder has been often taken for granted. Today, however, in metallurgical laboratories, solder is the subject of exact scientific study and analysis. This quantometer is used to test and record the exact amounts of various elements present in solder alloys. Every lot of solder produced is tested for compliance to rigid government and commercial specifications. The spectrograph serves as a further safeguard against the possible presence of foreign material, thus ensuring the absolute purity of the solder product. Today, solder is available in many forms, from larger sizes called ingots to the minute preforms, which are used when a predetermined amount of solder is to be applied. Powder and paste forms provide ease of application in those hard-to-reach areas. Solid wire and cord solders are offered in a variety of sizes and diameters. Solder is an alloy, simply a mixture of tin and lead. But what makes this alloy so useful is a quirk of nature. Notice the melting point of solder is nearly 100 degrees lower than that of tin or lead. Here is a combination of two metals that for some reason will melt at temperatures nearly 100 degrees lower than the two metals it's made of. No one can tell you exactly why this happens. It's simply one of those unpredictable quirks of nature that the human race, without completely understanding, can harness to its own advantages. But why is this phenomenon so important to us? The answer is simple. Here is a sheet of pure lead and a rod of pure tin. Both have relatively low melting points. But through the miracle of solder, They are bonded together without the danger of melting the tin or the lead. For example, the seams of an ordinary tin can are soldered together and without damaging or melting the tin. Now let's see how solder works. Notice that on this sheet of copper, as the solder melts, it flows smoothly to form a thin, even coating. Solder is not a glue. When the copper was hot enough to melt the molten solder actually dissolved small amounts of the copper and then penetrated its surface. In this cross-sectional drawing, we can see that the molecules of the two metals have actually blended together here to form one new metal, which is part solder and part copper. This mixing of the molecules is called the wetting action. To obtain good wetting action is not always that simple. On this thoroughly clean sheet of copper, you will notice a marked difference in the reaction of the solder. It seems to ball up and not flow smoothly as it should. A cross-section would show large areas where the two metals have not blended together. The mixing of the molecules, the wetting action, has not taken place properly. In the first demonstration, the two metals are permanently fused together. Because of good wetting action, the solder is completely embedded in the copper and cannot be pried off. But the solder in the second demonstration is easily debonded from the copper. But why should good wetting action occur in one piece of copper and not on the other? The answer is simply air. When a clean metal surface is exposed to air, a chemical reaction occurs called oxidation. When heat is applied, as in a soldering operation, the oxidation is greatly speeded up and produces a non-metallic film that will prevent solder from touching the base metal. This film of oxidation makes good wetting action impossible. So even though our metal had been cleaned thoroughly beforehand, the oxides in these areas formed while we heated the copper and prevented the solder from bonding. These oxides must be removed or prevented during the solder operation. For this, we use chemicals called fluxes. There are many types of fluxes. However, only those derived from natural rosin are acceptable in soldering electrical connections. When the heat required for soldering is applied, the surface of a clean metal will quickly oxidize. The flux must dissolve and remove these oxides. As you can see, the area around the flux has discolored, while beneath the flux, the metal is clean and ready to accept solder. For ease of application, solder and flux are produced in a combination called core solder. The rosin flux is contained within the solder itself. Cored solders are manufactured with various core designs. With this cutaway model of cored solder, we are able to see exactly how the solder-flux combination can work together. The flux must have a melting point lower than that of solder, thus enabling the flux to reach the metal first and prepare the way for the solder. As the solder melts, it displaces the flux on the clean surface. Flux also helps solder to flow as it should, then rises to the top and is pushed to the outer edges, carrying with it the oxides it has removed. Also, rosin flux is non-corrosive. After cooling, its action stops and leaves clean connections like these. An acid flux will continue to corrode, and worthless connections like these are the result. Also, rosin flux residues are non-conductors of electricity, thus removing the danger of shorting out these connections where the flux has flowed between them. It is good practice to remove the flux residue after soldering. This eliminates the chance of the residue collecting harmful dust particles and leaves clean, neat connections. In any solder operation, a heat source is needed, such as ovens, stoves, torches, and heaters. Or for specific applications, resistance units are used. Conduction-type irons come in various sizes and are probably the most commonly used type of heat source. The more you know of the equipment available to you, the easier it is to choose the right tool for the job. The conduction-type soldering iron consists of a few simple parts. The cord passes through the handle to a heating element, which in turn transmits the heat to the tip of the iron. The tip stores the heat and through conduction passes it on to the work. The tip of a new iron must be prepared before being used to solder. First, the iron is dipped into liquid flux, then into a bath of molten solder. This process of preparing an iron is called tinning. A clean cloth may be used to wipe the tip of excess solder, leaving a thin, even protective coat. However, normal use will produce a buildup of oxides and dirt on the used tip. Simply applying rosin-coarse solder to the used tip is another method of tinning an iron. This coating of solder on the tip greatly increases the transmission of heat from the iron to the work. Tinning also keeps the tip clean, which is imperative for clean connections. Reliability depends not only on the tools and materials, but on the sincere efforts of the individual technician. With a thorough understanding of your tools and materials, the next step is to acquire the proper technique with which to use them. The way you hold the soldering iron is up to you. Comfort and ease of handling are most important. But proper technique is the way you use the iron. For good wetting action, the metal to be soldered must be as hot as molten solder. For this reason, we heat the connection and then apply the solder. The connection actually melts the solder. Never apply the solder to the iron. The flux contained in the coarse solder is burned away and does not have a chance to clean the connection. If you have chosen an iron of proper size and wattage, the connection is heated almost instantly. So the application of the iron and then the solder is almost simultaneous. Again, never apply the solder to the iron. Wire wrapped around a terminal is not a solid connection. The two metals actually are not even touching. A film of oxidation holds them apart, but solder makes them perform as one solid metal. Remember, heat the connection. The connection must be hot enough to melt the solder, or the solder cannot blend with the other metals. Wait a minute, the iron was removed too soon. Because of insufficient solder, the wire and the terminal cannot perform as one solid metal. So if this assembly were allowed to be completed, that connection would be the weak link in this chain of electronic components. With the assembly mounted on this vibration table, we can simulate conditions present in airborne electronics. The continuity of electrical impulses passing through the assembly registers on the oscilloscope screen. At a low rate of vibration, the reaction is good. But as the rate of vibration is increased, a malfunction begins to show up on the screen. The electrical continuity has been broken. So unless the wire wrapped around a terminal is properly soldered, it cannot act as one metal. Under vibration, the contact is repeatedly broken, causing the failure of the entire assembly. Although the connections differ from the terminal type, the technique of soldering on a printed circuit board is basically the same. The iron should be applied to heat the lead and the pad at the same time. Remember, for good wetting action, the connection must be as hot as molten solder. If the connection is hot enough, it will melt the solder. Without enough heat, the solder cannot fuse with the other metals, and a cold joint will result. A cold connection cannot function as one solid metal. But as long as the connection is hot enough to melt the solder, there is little danger of a cold joint. A small amount of solder applied to the tip of the iron will help the transfer of heat, but be careful, the solder must still be applied to the connection. Notice the flux has been pushed to the outer edges, carrying with it the oxides it has removed. After cooling, the solder should have a smooth, shiny surface. Be careful not to overheat the connection. Too much heat could debond the pad from the board. Never apply the solder to the iron in hopes that it will run off onto the connection. The flux is burned away and there is no wetting action. Heat the connection, then apply the solder. Allow it to cool without disturbance, and you will have produced a reliable connection. Be careful not to jar the connection while it's cooling. This could produce a fractured or cold joint. Now once more, watch the proper way to solder on a printed circuit board. Good technique will always produce a reliable connection. Before installing stranded leads, the cups of a plug or receptacle must be first partially filled with solder. With the plug mounted at a 45-degree angle, you heat the cup and slowly feed the solder into it. The flux, which melts first, cleans the inside of the cup and then is pushed to the surface by the molten solder. Then the pre-filled cup must be reheated and the lead inserted. Be careful not to move the lead while the solder is cooling. You will fracture the connection. But here we have another serious problem. The solder has run up the wire and under the insulation, causing the wire to be stiff and brittle. This capillary action is called wicking. Now the stranded lead is no longer flexible and will easily break. Wicking is generally caused by too much heat. This tool is designed to grip the wire below the insulation. It helps to drain off excess heat and prevent the solder from running up the wire. The wicking tool also helps to hold the lead steady until the solder solidifies, which lessens the chance of fracturing the connection. Notice that without wicking, the stranded lead remains flexible. When installing leads, special care must be taken to avoid burning the insulation of wires already installed. Do not remove the wicking tool until the solder has solidified. Trying to use an iron on these small cups would cause damage to the adjoining leads. A better choice of tool would be a resistance unit. The transformer regulates the current, and the foot pedal, or in this unit a hand switch, allows us to use the current only when we need it. Resistance units do not store heat like a conduction type iron. When the switch or foot pedal is closed, a small amount of electric current passes from one tip to the other. The current passing through this small rod causes the rod to heat rapidly. With a resistance unit, you are able to pinpoint the heat, thereby not endangering the surrounding connections. When the pedal is depressed, only the cup between the tips will be heated. Be careful you fractured that connection. By removing the wicking tool before the solder had completely solidified, a fractured joint will result. It's easy to see that this connection cannot perform as a solid piece of metal. In most cases, a fractured connection can be repaired by reheating the cup. Hold the wicking tool steady until the solder has solidified. Now, once more, let's prepare a connector for installing leads. Notice the flux, having cleaned the cup, is then pushed out at the top by the solder. This action is vitally important. If there is insufficient heat, the flux cannot escape and will form a rosin pocket at the base of the cup. A rosin pocket will seriously affect the conductivity of the connection. But if you're careful to feed the solder slowly and maintain sufficient heat, the flux will all rise to the surface, allowing the solder to settle in the cup, leaving no vacant or void areas. When the lead is installed, there must be sufficient heat for good wetting action, and the lead must be held firm until the solder again solidifies. This one unit has over 16,000 soldered connections. One bad connection and the entire unit is worthless. To achieve reliable, dependable soldered connections, three things are important. First, thoroughly know and understand the tools and materials available to you. You want the right tool for the job. Second, master the proper technique with which you use those materials. There is no such thing as good enough. You must be an expert. Third and most important, you must understand the seriousness of your job. You may never know what will depend on the connections you have made. This is not the end, but we hope the beginning of more reliable soldered connections.